everyone. This is our first event of the year. We took a break for the past 3 months. We were reorganizing and, just taking a break. And now we are back. And our first event this year is going to be about creativity and AI. And we could not be more excited. And if you haven't checked us out already, our website is AIxDesign.co. You can follow us on our socials to get more information about what we do. So, without any further ado, let's get started with our keynote, our first keynote this year. So, today's event is with Stefan. He's the director of the Asimov Institute and a professor of artificial intelligence research group in Netherlands. He's also the senior advisor to the Netherlands AI Coalition. And in his research, he explores how prediction relates to understanding and how machine learning can be constrained and whether creativity can emerge from machines. So, Stefan, the stage is all yours.
Yeah, thank you, Avantika. Let me start with sharing my screen, which is typically the most difficult step in any talk. Can you see my screen now?
Yes, we can see that. Yeah.
Great. Then I think we can get started on this topic. It's a very interesting topic. At least that's what I think, and I will try to convince you of this in the next 30 minutes or so. So when we sit down together to discuss creativity and computation as it relates to AI, we often think about the visual arts, computer-assisted design, automated music generation, sometimes automated scientific discovery as well. I find that a much overlooked domain of creativity is actually humor. So we can start there in this talk. Now, if you happen to have finished your PhD in artificial intelligence during the last decade, as I did, you will have found yourself overwhelmed by all the interesting career opportunities that emerge. In 2015, I was approached by Apple Research Labs to work on Siri, which is Apple's voice assistant, as you probably know. And during the interview, they showed me the following example. Now, I don't know if you've ever asked your telephone this question, but this is what Siri answers to this question. And to be honest, I was quite impressed by Siri's sense of humor. I was thinking, well, here at Apple, they must work on some pretty sophisticated machine learning to come up with such a clever answer. And then I found out that why they wanted to hire me, which was to write these jokes myself for Siri. Because of course, Siri couldn't make up a joke like this in a million years. And I was kind of upset. And I guess you could say after all those years of PhD research, I was disappointed in the challenge they gave me. So I turned down the job, which of course in hindsight was a huge mistake. Would have been a dream job to work at Apple. But when we sort of zoom out and look at computers that are trying to be funny, I think Siri is no exception. In fact, if we dive into the scientific literature, we can find, for example, this pun generator. So these are all jokes or puns generated by a computer. I'll leave it up to you to find them funny or not. I don't think they're bad necessarily, but it's important here to realize that in total, 188 puns were generated by the computer with, of course, human input about semantics of these words and what rhymes, etc. And only a very small portion of those 188 puns were actually rated as funny. So if you go into the paper, you see there's only this on the right side, this 5-point score. It's a very small number of jokes. So most jokes actually were unfunny, but you never see them because the authors selected best jokes for the paper to impress their audience. And then I select the funniest of those to impress mine. And so I think overall, it's quite a human selection bias that's going on there. So even though these jokes might be funny and they're also functionally generated by a computer and they're creative in some sense, we can still ask ourselves who or what was funny, or in other words, where does this creativity originate? And in this talk today, which is divided into 4 parts, I will try to uncover a hint of the answer to this question. Which brings us to part one, the unusual story of the first computer ever built and the role that Napoleon Bonaparte played in its existence. So although the first computers as we know them today were only built during the Second World War, so a little over 70, 80 years ago, the original design of the computer dates back to 1837, and when the British inventor Charles Babbage discovered the analytical engine to quickly and easily calculate logarithms. His co-worker there was Lady Ada Lovelace, who was daughter of Lord Byron, a poet, and also the world's first programmer. What is less well known is that Babbage, in turn, was inspired by an even older machine, which we see here. This is a replica. This automated chess robot was built as early as 1770 by Wolfgang von Kempelen. And it could not only play chess, he often won its games. And so for over 70 years, this robot was touring palaces and courts and played chess against very famous people like Benjamin Franklin, Napoleon Bonaparte, Frederick the Great, and also in 1819 twice against Charles Babbage. And Babbage lost both games to the robot. Now the game against Napoleon was especially noteworthy. Napoleon played with the black pieces, but in order to surprise the robots, he made his first move. And then the robot played on. And now shortly after, Napoleon made a move that is not allowed in the game of chess. And then what happened was that the robot picked up Napoleon's piece and placed it back on its original field. Napoleon moved the same piece again to the same unauthorized field, and the robot answered the move by picking up the piece from the board again, but now placing it next to the board. Napoleon made an illegal move for the third time, just to see what would happen. And then with one fell swoop of his arm, the robot swiped all the pieces off the board. According to the eyewitnesses of this game, Napoleon was amused, and then he played a new game, according to the rules, which he lost in 19 moves. So, big puzzle, what happened? How does this work? Well, it was only after the robot was lost in a fire in 1845 that the answers to these questions became clear. It was the son of the owner of the robot who finally revealed the illusion, which is that the space under the chessboard was just big enough for a small human chess player who could move the pieces around with tiny magnets and strings, which is of course disappointing, but let's not forget that this indirectly led to the birth of the computer, which is able to play chess. Now, what's the takeaway point from this story? I think this historical anecdote teaches us two things. First of all, creativity is about more than just predicting the best move. And second of all, when you see a creative machine, ask where the human is hidden. So let's move on then to the second part, which takes place in the 1970s. When a group of biology researchers, they devised and conducted experiments to test if chimpanzees could learn to understand language. Now, these researchers were able to show how different language acquisition strategies explain varying learning curves between the apes. So previous to their work, other studies already showed that apes could learn a vocabulary of well over 1,000 different words. And a vocabulary for chimpanzees looks something like this. So they don't use letters, of course, they use like these pictures, which we call lexicograms. And they're typically used in these kind of experiments. Now, what has to happen is that an ape has to press or point one of the lexicograms with its finger. And then it indicates that it wants to use that word. It shows that it can use language. And so, for example, it might point to a lexigram that stands for banana, and then subsequently point to the sort of give words, because you give a banana. And then if it does both, if the chimp does both, then it gets a banana as a reward. And the same goes, for example, for drink, water, etc. So you have to know the relations between these two words in order to get a reward. Now, using the training method, such as the one I just described, apes can be induced to learn large vocabularies. But what we see is that as the number of studies grew over time and the gathering of experimental data continued, some researchers started to doubt the validity of the claim that these apes were actually using language as language. The sentences were produced without error at some point, And given the limited set of words and sentences, the behavior of the apes couldn't be discerned from humans performing the same task. Of course, that's something that we also see in computers and AI now and then. But what the researchers questioned was, do these chimpanzees actually understand the lexicograms as symbols, so as standing for something else, or are they just stimulus response pairs? In other words, if I press these two buttons, I get my reward without knowing what the button stands for. So they might not mean anything to them, even though they can sort of perfectly predict which buttons to press. And so the researchers devised an experiment to test this. Initially, the chimps were required to name shown objects by pressing the correct lexigram token, the correct word, and then they were immediately rewarded. And then, surprisingly, the apes often fail to learn the simple correspondence because the purpose of the exercise was not salient. There's a case reported where a chimp is lying down on its back and then it just presses a button by mistake, but it happens to be the right button to press. And then from there on out, it just lies on its back trying to sort of move the keyboard because it thinks it's getting rewarded for lying on its back and pressing a button. So not only do you not have to know which button to press, you also have to have the sort of the context of what you're actually doing. You're actually, communicating. Chimps don't even know this, of course. It's something very human. So it's almost like a superstition of lying on your back that develops over time. And then it becomes really difficult to unlearn a superstition again. So the researchers in their paper, they really described the difficulty they had in these first steps. Now, no matter how obvious the function of a button may be for us humans, the chimps fail to notice how to operate the board because there's so many possible cases or causes for a reward. So then they changed the setup, which did allow for the chimps to notice the relation between objects and lexicograms. At first, they did it with one button, and then when they learned the buttons, what they meant, they tried to do this two-word sentences. So give banana, drink water, etc. And then they added more and more buttons and longer sentences. And then something interesting happened, namely that some of these apes actually slowed down their learning and started making more mistakes. And I had a very difficult time of producing longer and longer sentences, whereas other apes somehow got it. And they had no difficulty whatsoever of making longer sentences, and they virtually made no errors at all. So they were able to keep up. Now, what the researchers concluded is that the failing chimps, they tried memorizing the growing number of stimulus response pairs. So as their number grew and grew, they started to make more and more mistakes because your memory is limited. And then it also takes more time learning correct predictions because it's just more combinations of words possible. Whereas the successful chimps, they took a different approach. They actually understood what a lexigram meant and what it stood for. They had a relationship between the lexigram and the actual world, which they constructed. And this was an initial investment, of course, in learning, but then it pays off at the end. Because if you know what it stands for, it's easy to memorize. And then you can relate the words and sentences to the knowledge about the world. And this allowed them, over the long run, to learn more efficiently and memorize more sentences. Now, why is this interesting in the context of AI? I think it points out something very fundamental and maybe also something that's very fundamentally wrong in AI, which is the difference between predicting and understanding. So, and I think this is a question that's often overlooked, but with particularly when you focus on creativity, you just have to get into this question and try to answer it. Does prediction also apply understanding? Or in other words, if I can predict how a system behaves, perfectly predict, do I understand the system? If I predict how pressing words on these lexicograms, if they lead to a reward, do I understand the words? Or in the chess context of the first story, if I can predict the best next move in chess, do I really understand the game of chess? This is a question I hardly ever find answered or even asked in the computational domain, because if you're in control, meaning that if prediction does imply understanding, it also gives you a sort of certain level of power. You have full control over a system, and admitting that prediction is not equal to understanding is really problematic. I think the Turing test also shows this. Okay, I'll come back to this a little later. First, I want to give a quick introduction of some work I did in this field. So some cases with creativity and AI. So I'll start with 2015, some 6 years ago, when I began the Asimov Institute as a place where we can sort of freely explore the potential of AI in creativity and art and design. So we work together with scientists, artists, designers, engineers, to just sort of play around with this. As you know, AI has been rapidly coming up in the last decade or so, become more and more popular. I mean, 10 years ago, I had to explain at the start of a talk what I meant with artificial intelligence. 5 years ago, I had to explain neural networks. Now I don't have to explain anything anymore. So it just shows how fast it's going, as you all probably also know. So in 2015, we were still sort of explaining neural networks, and we published this, which is the Neural Network Zoo. It's essentially a sort of a lookup table or a cheat sheet for neural network research. And we made it for ourselves, just to sort of figure out which of these networks we could use for generating stuff. You know, if you work in creativity, you're interested in and not so much classification or regression, or, you know, you don't want the output as a number, you want the output as a visual depiction, a movie, audio, whatever, something like content. And some of these networks are actually pretty good for this. So the generative adversarial network is one that is often used now. It's become more famous for instance, for deepfakes. This is typically the technique that is used. But there are also all types of autoencoder, variational autoencoders that are also very interesting when it comes to generating stuff. So we made this to help us investigate, and it actually it sort of went viral in the AI world, which makes us very proud, because lots of people found it interesting to have this, and also nice to hang up on their wall. So we now have a poster store which you can go visit and buy a poster of one of these. I'm not asking for sponsoring here. I just want to point out the possibilities. But then we use this knowledge in one of our projects, which I want to share. And this is a project which we called Predicting Fashion with AI. It's about 5-6 years ago. I did it together with Amber J. Sloten and Fjodor van Veen, who were sort of collaborating at the Asimov Institute back at the time. And Amber is a virtual fashion designer. We met each other at the University of Applied Science in Amsterdam, and now she works for the virtual fashion house, The Fabricant. The question we asked in this project was, can we predict next year's fashion using AI based on this year's fashion? And it was just a curiosity question. There was no real outcome necessary. We thought it might shake up the fashion world a little bit if we get something interesting going. It was just an interesting proposition, because if we could predict next year's fashion, then either our AI was very creative, or the fashion industry was not creative at all, or neither was creative, of course. And all those outcomes would have been interesting. And also we thought, well, if we can predict fashion, it means we can sort of understand fashion. And that was also, I guess, also on a personal level, like, what is going on? What is fashion? At least that's what we thought. So what we did is we gathered a data set of these kind of images that you see here. 500 of these images. We used a deep convolutional GAN, one of these beasts in the neural network zoo. Very small setup, 20 hours on a single GPU processor. I'm almost embarrassed to talk about this now, but I can hide myself behind the fact that this was 5-6 years ago, and it was just a small hobby project. But we got some interesting stuff, at least from back then. So the way this technique works is it projects these designs, which you see here. It projects them into something called latent space. So you can almost imagine this as a game of baseball, where the AI or this neural network, it throws a pitch. And then what we wanted is to throw a pitch in almost the same spot in this multi-dimensional space. What you see here is, of course, 2-dimensional space, but in reality, it's n-dimensional. These models have almost infinite amount of dimensions, but it's very hard to draw on 2D. So I'll take 2D for now. So imagine that these designs of all possible places to end up, they end up in more or less the same space. And if I have a different fashion design, it would end up somewhere else in this space. And that's a learning task for this neural network. It's like it's learning to pitch to the right spot. Now, if you have this set up, with some of these networks, you can actually turn them around. And this makes them generative. And what you do then is you sample from this space in this particular location. So let's say I ask the network, instead of pitching a ball to this space, trace back the trajectory of the ball from this space to your retina. So I don't want you to classify an image, I want you to generate an image. And then we asked this network, once it learned these images that you see here, we asked it, give us more of this stuff, but not the same. And so the network gave us this after about 1 day of training, which is not, of course, a fashion design in itself, but Amber was really excited about this. I mean, she's the artist, she's creative. It gave her tons of different ideas. So she used this as a basis for further explorations into her collection. So just to give you an impression, so on the right, you see the image that was generated by our algorithm. And then in the middle, you see the design that Amber made out of it. Here's some other examples. Here's one that's animated. So did we succeed in our original goal to predict next year's fashion? No, probably not. But we did get some interesting results in how do we collaborate? How does a sort of hybrid system of an algorithm that learns and then sort of opens up a space of possibilities, and then a human designer which explores this space of possibilities and then makes a collection out of it. How do we fit these things? And I think that was a very interesting result in itself. We also found that just as the chimpanzees, the computer sort of acts like a chimpanzee that tries to predict. It's not like a chimpanzee that tries to actually understand. And that's not the computer to blame. The computer doesn't have access to the sort of underlying semantics of fashion in this case. It doesn't know what works well, what doesn't work well, because we don't show it. We only showed it the data set. Same with the chimpanzees. So it knows what buttons to press in order to get a reward, but it doesn't understand the real subject. And this requires a human in the loop. Now, and we know that we can get, just like we did in this project, very interesting or inspiring results from AI. I just want to show you some. For instance, this one. This is from an earlier presentation that I did a couple of years ago. These are all cats that don't exist. You might wonder, why do we always get cats and dogs in these examples? Well, that's because these algorithms are all trained on the internet, and just so happens that the internet is full of cats and dogs pictures. So that's why you always see cats and dogs and never an elephant or a tiger. So these cats, if you think I recognize my own cat, it's not the case. These are all imagined by the computer. They don't exist. And then when I was a couple of years ago giving a presentation on this, I realized this is very old. Like, state of the art is much better. I mean, this is what we had like 2 years ago. It's a website called This Person Doesn't Exist. You might know it. If not, definitely worth checking out, because it just generates these people which don't exist. So I didn't have to ask permission to use their photos, which also is a very interesting property. Now, we talked about latent space, about pitching. What's interesting is that we represent these entities in a numerical space. So we can sort of ask the pitch back, sample from this space, but we can also imagine all kinds of transformations, because ultimately these are just vectors or numbers in space. So for example, I can say, well, I have one part of this space which is, occupied by dogs, another part which is occupied by flowers. I can sample from it. I can also average a dog and a flower, and then ask for a pitch back, and I get something like this, which is completely made up by the computer. I can do the same thing with dogs and water or geysers. I can, even if you imagine what it would look like if you cross over a cappuccino and a dog, you get something like this. Endless possibilities for creatives, I think. There's another one, which is more recent, which I want to show. This is the earlier one, 2016. You ask the computer, give me an image of a bird with a black head, a pointy orange beak, and a yellow body. Now, this is what you get, different locations. And then 5 years later, we get this, as recent as 2 months ago, more or less. Show me an armchair in the shape of an avocado, or an armchair imitating an avocado, and you get all these kind of results. And again, no human intervention. This is just what you get from the text. And for me, this is completely sort of this really blew me away. There's other examples. I really recommend checking it out. And I'm showing them because it's interesting for two reasons. First of all, because everybody should know about these, but second of all, just look at the speed at which this is developing. I mean, the cats and this person doesn't exist was 5 years difference. This also, the difference between this armchair and this and these images is just 5 years. So just imagine what this could mean 10 or 20 years from now, where we are at, and the possibilities. I don't think we've even started exploring them. So I'm deeply fascinated by the potential of these systems. And if you work in the space of art and design, like to collaborate or just get in touch, I'll share my contact details at the end of the presentation. For now, I'd like to move on with the final part of this talk, part 4. Instead of talking about creativity in machines, we're going to do something different and turn our attention to experiencing the machine in ourselves, and maybe through that experience the creativity in the machine in ourselves. So let me open with Harari, very interesting thinker. In his book, Homo Deus, he describes how responsibility for making decisions shifts or is shifting from the human mind to algorithms and data. So you used to rely on your own feelings and instincts to drive from the city to the airport, but now you can use Google Maps. You learn to trust Google Maps instead of your own intuition, which ultimately prevents you from navigating to the airport with your own knowledge. And I think we're familiar with this feeling. So intelligent algorithms can plan routes better than we can. It can play chess better than we. It's better at recognizing faces or generating faces. And in the near future, it will also be better at recognizing our own feelings than we are, which is something that Harari points out and is very essential. It's very important, I think. And then we can use this capacity of AI to also generate new stuff, new designs, personalized, very efficient, very cheap. But as we saw earlier with the chimpanzees, quality requires something more than just prediction. It also requires understanding. And I think Picasso is someone who also pointed this out very early. Because when Pablo Picasso was first shown a computer in 1968, his response was, computers are useless, they can only give you answers. And I think he proved partially right. So computers are useful for prediction from data. But he's right in that they can't ask the right question because they don't understand the data. Now, we can talk about this, but I think in order for you to understand this, in order for us to understand this ourselves, it's better if we sort of experience this idea. And therefore, I'd like to end my presentation with a little performative experiment, which I call the algorithm, where I'm first going to read an instruction to you that we'll use to sort of build up a meditation pose. And I invite you to participate in these steps. If you want to join in on this experiment, please do. And if so, then I'm going to ask you to either tie a sleeping mask around your head or a blindfold, or put a towel over your eyes, or otherwise you can also close your eyes, which is of course fine. And if you don't want to, you can leave them open. And then we're going to build up this your posture. Because the idea of the exercise is to calm down your thoughts, allowing you to peek inside. And then we're going to try to solve a riddle the way a computer would. So it's about introspection. All right. So we're going to build up your posture. So you rest your feet and you start by feeling your feet resting on the floor. Now put your hands on your legs and feel the weight of your body in your seat. You keep your head upright, eyes closed, but very present here in your unmoving body. Mouth closed, jaws relaxed. Breathe through your nose as it comes spontaneously. You take a breath, and then almost by itself, you breathe out automatically. It's breathing, not me. Let your shoulders hang down and put your thoughts into your stomach. And from the power that sits there in your stomach, put aside everything that had you occupied. When you're sitting like this, any thought is welcome. And almost by itself, without any effort or intention, your attention goes back to your breathing. There's only this. And from this state, from this position, the riddle follows. Try to look inside and follow your thought process. This is the riddle. You're standing in front of a closed door. On the other side of the room, on the other side of the door is a room where 3 light bulbs are hanging from the ceiling. The room has no windows and is completely closed off from the outside, apart from the door. On the outside of the room, just left of the door, are 3 light switches. Each light switch is connected to one of the 3 lights inside, and the lights are off initially. You're allowed to use the light switches, but after you open the door, you go inside and you can't use the switches anymore. The riddle is this: how do you discover which light switch belongs to which light bulb? And so maybe you've already discovered that there's no combination of light switch modes that can provide an answer to this riddle. And at the same time, you know that there is probably a solution. That's why it's a riddle. So a possible answer to the riddle might be, you turn on a light switch, you wait a few minutes, and then you turn it off and you turn on another light switch. You enter the room and you feel the lights. The light bulb that is warm is connected to the switch that you turned on for the first time. The light bulb that is on is a second switch you turned on, and the final light bulb is controlled by the switch that you haven't touched. Now, this intuitively feels like the right answer, but it's certainly not the only answer. You could have also thought of drilling a hole in the door or call a friend who happens to be standing in the room. But somehow, for you, probably, the first answer feels better. How? And with that question, you can open your eyes again if you had them closed, or remove your towel or blindfold. The performance or the experiment is over. And I'd also like to thank you for your attention and close this presentation.
Nice. Thank you so much, Stefan. I'm still figuring out the light switch solution. Nice. Thank you so much for sharing all your thoughts on creativity, and actually way beyond that. I got some really nice, interesting comments on chat as you were speaking. So I'll touch on a few of those. And then I think we have 20 more minutes for Q&A. So if anybody has questions, please share them on the chat. So I'll just quickly go through some of them that were shared as you were speaking. So Jenna was saying, I wonder if this was the original human in the loop automation. Probably, yeah, like Wizard of Oz before we made that a prototyping thing, but actually as a solution. definitely still happening. Also asking, are you familiar with Emily Bender and Alexander Kohler's paper on ACL last year on meaning and natural language processing? It does look at that problem.
I'm not familiar with that paper, but if anybody could send it to me, then please do, because it does sound very related.
Yeah.
Of course, meaning in computation and AI is a subject that's been going on for decades. The symbol grounding problem, I think that's how the problem was framed back in the 90s. How do you connect computational symbols to the real world? I think that's a problem, that's a frame that we're still in. And it's connected to a lot of these other problems. Also, I think to the framing problem, for example. So my gut feeling is if you solve one of these problems, you probably solve them all. But we're not getting very far with computers.
Yeah, I feel like currently a lot of this discussion is also around language, obviously, because it is one of those things we have that are symbols of the world that we use and we try to, NLP is pretty developed. Do you think in this challenge shows up in language differently than it might in other domains?
I think so too. I mean, I didn't show you all the projects that we did, of course, but we played around with vision, with movies, moving images, music, and also language. And out of these 4 typical content types, it just feels like language is by far the most difficult one.
Yeah.
Now we've seen GPT-3 and sort of the amazing properties that it has. And this has been around for a bit longer. There was a famous Shakespeare Generator a couple of years ago, which also got some attention. What's different, I think, with language, with these more visual images or these visual types of content, is that it only captures the syntax of language. So with the Shakespeare Generator, if you read it without attention, without going behind the words, almost like these 8 bits with pressing the lexicograms, then you recognize Shakespeare immediately. If you read it beyond the words and you move into the semantics, if you move your attention into the semantics, and suddenly it all falls apart and it's a completely senseless story. I think with more data, more processing power, you can probably move further and further beyond the syntax towards the semantics, but it's still a syntactical approach. And so my gut feeling is that with these language content types, you're never going to get very far with modeling semantics or recognizing semantics, because there just is a lot of depth in these types of contents. The whole point of symbols is that the words don't look like the things that they represent. In the case of images or video, there's actually structure in the message. So the content contains the structure of the world. It's iconic to the world. And so I think there's a lot more semantics to mine from the message itself, which is also why the AI is so successful in the visual domain and probably also audio domain, but audio is very difficult because of time. So that's a completely different type of problem. Yeah.
Nice. Thanks for elaborating on that. Maybe we can talk a bit more about your work on music as well, because I know you've done quite some work with like generative audio, and I think it's a lot less sort of talked about than GANs. So maybe we can chat a bit more about that later.
Yeah.
I'll just go through these now. So there's a lot of love for the neural network zoo. People being like, I love this chart. It's on our teacher's wall.
Oh, that's very nice to hear. Yeah.
Yeah, I think I've also seen it just pass by everywhere before we ever met. So that went pretty far. Someone's referencing Daniel Dennett and like his theories on competence without comprehension, sort of also as a lens on, I guess, what you call prediction and understanding. Are you familiar with his work?
Yeah, of course. I've met him when I was back at Tufts a couple of years ago. I mean, when I say I've met him, I've had the opportunity to talk to him, not the other way around, of course. I mean, he's incredible. He's a brilliant philosopher. He's a great thinker. I think he puts a bit too much hope in the computation. So one of his most famous books is called Consciousness Explained. And sometimes it's jokingly called Consciousness Explained Away, because what he's apparently doing is he's saying consciousness is an illusion, it doesn't exist. And then the next question is, okay, but an illusion to who? And so you end up in the cycle of yes, but it's still there. So I don't think the challenge is to sort of prove that people are not conscious or that everything is conscious. The challenge is, why am I conscious and why is my table or my chair not? And there's a difference. And where does my computer sit in this spectrum? And I think in order to answer this question, you do have to move beyond the computer, because it's a very functional device, but it's very limited. And it's also something I try to sort of, hint for with this difference between prediction and understanding. The computer just functions differently from we do. And I think we can actually build conscious machines at some point, or sentient machines, but it won't be a computational architecture. And I think Dennett does think that computers are the sort of the ultimate tool.
Yeah, the hard problem of consciousness. I think that's for another chat.
Yes, please.
Vera is asking, I like this one as well. We've talked about this. Like, do you see the creativity of some of this work only in the network's output, or do you also take the creative process of either the network or the artist that works with the algorithm into account? So more about creativity in the process rather than the algorithms or the models themselves. And when it comes to GANs, how do you decide the output is creative and not just the average image based on a visual data set? So I guess some of the curation in some of this work.
Well, so I think that's two questions, right? So the first one is the way we worked in our projects is that we really first start with diving into the creative process of the designer. One thing that we found is that creatives have their own unique processes. And we don't want to build tools where they have to change their processes. We want to build tools that really support their mode of thinking, their way of thinking, because the automation is the easy part and the creativity is the hard part. That does bring a problem, like how do you design these tools? Like how do you design a tool? You don't have the resources to design a tool for everyone individually normally. The good thing about the Asimov Institute is we did have the time because we didn't care. So we just sat down, we had multiple sessions of going through the creative process. And with Amber, we found something different from, let's say, Gecko, who's a DJ, where we did music production with. If we have some time during this hour, I can maybe show you some samples of this music generation. But we found they had completely different processes, so there was no point in making one tool for them or something. How do you, put this in the market and commercialize? I don't know, because it's of course not. There's no way you can pay for that, but for research, this is the way we worked and the way we like to work, and then you end up with a sort of a hybrid system. And so for the second question, which was
so it was sort of about how, well, when you're creating visuals using GANs, how do you decide on which output you consider creative? So some of this curation, which I think is a big part of it.
It's a good question. Typically I think in literature you see that creativity is divided in two parts. Sometimes it's defined as surprise. So you say the more I get surprised, the more creative something is to me. But I think another way of looking at it is it's comprised of both novelty and value, or originality and usefulness, those two elements. I think the novelty bit we can do pretty well with computers because we have a random seed that we can just put in. And we can also tell it, if you remember the latent space image, we can tell it, do I have to be right in the middle, or can I sort of spread out from this point clouds, and how far should I spread out? And in some way you could say that's a kind of originality. It's not the full thing because you're still in a space that's predefined. I think if you're looking for real newness, you have to break open the space. You have to get out of the box, and that's a completely that's not a computational question. It's not something you can solve with computers. But let's say within the computational domain, you can ask the computer to explore this space and be more or less novelty driven. When it comes to usefulness, I think it's more difficult because you have to insert value, and there's always value to someone, and there's never value to something. So that means that either I as a human have to provide a fitness function beforehand or structure things in a way that something valuable always comes out, or I have to do selection like we did with the joke generation at the start. You just you generate a whole bunch of random stuff, and then you sort through it manually. But that's also, of course, faking it. There's no value in the computer, and the computer doesn't care if something is pretty or not, or good or not. I mean, it doesn't care about anything. So you have to have this human element, I think, for value in searching.
Yeah, to decide what's interesting. Yeah.
Yeah.
Would be interesting if anybody knows if there's any projects where, I don't know, they train the model to evaluate GAN outputs and like select the interesting ones. So actually trying to have a computational curation, because from what I've seen, it's like, yeah, output loads of stuff, and then the human sort of picks out the interesting bits. It's obviously fine for now, but it would be interesting to see if that's something we could also train a computer, just like what's aesthetically pleasing, or what's sort of this balance you say between like novelty and familiarity, which it's funny you opened with joke, because I think humor is that, right? It's like understanding patterns and then breaking them a little bit. So yeah, I think there's
humor is a very sort of uniquely creative exercise. There's a book called The Act of Creation by Arthur Koestler, where he says basically you have art, science, and humor as 3 types of creative acts. So I think it's sort of undervalued at the moment, but it's interesting to look into. As for this feedback loop, there's one idea that I had for some time, but I never managed to organize it. So maybe someone wants to pick it up. That's that you can do the sort of the value insertion with the participant or with the consumer. Or so imagine a setup where you have a museum, you have this gun which is sort of continually generating new images, and then you have a camera or a sensor setup that measures the attention to these images from the audience, and then you use that as feedback to do value selection. So you get the novelty from the gun, and then you get the feedback loop or the value from the audience. And then maybe at some point you come up with an image that is so interesting that nobody will ever leave again, and then you have the perfect museum. I mean, that's the so I think these are the kinds of ways to look at value insertion. Yeah, you need a human in the loop somewhere.
Yeah, that's a cool idea. Yeah, if somebody wants to build an installation for that, reach out to Stefan.
Please do. Yes.
Nice. Ave saying, I'm curious to know your views on connectionism, so symbolist versus the embodied view of intelligence.
Yeah. Well, I think you need to know a little bit of history of AI in order to really follow
I love
this.
how you're just picking up on all the references, like it's, just like, oh yeah, I've read that.
Yeah. It's a very big story, and it's one story, so it's easy to remember all these parts. Originally AI was, the term was made up in the 50s. People thought it would take like 6 months to build a computer that was more or less equal to the human mind. It turned out to take more effort. And so this symbolic approach, sort of a programmed approach where I design a system that is just following the steps, and then it turns out to be intelligent and creative and maybe conscious, we don't know. This was the original idea. We worked on it for decades. We had some winters. And then, as always, like a last resort, like we don't know how to do this, people came up with these connectionist architectures, these subsumption architectures, like Rodney Brooks, for example, in the 80s. And this led to the symbol grounding problem. And so the way to define this is we have this intelligent system, a computer program in the symbol world. It works with symbol world. It works with symbols. They all interact. But the system itself doesn't interact in any meaningful way with the outside world because it doesn't understand the outside world. And the outside world also happens to be very unpredictable for the system, so it breaks all the time. So how do you ground this symbol system in the outside world? And then you can sort of use these connectionist extensions. And there's a hard cut. I've never seen any good example of, a connectionist architecture being sort of connected to a symbolic architecture and then working in a meaningful way, because there's always, the different languages. What's been happening recently in deep learning is that this connectionist approach has gained more and more attention. And now we're sort of, I think, entering into a decade where we see the reverse happening. So instead of the burden being on the connectionists to make this connection from the symbols to the outside world, the connectionists are in the lead. They have all the momentum, and it's up to the sort of the symbolic culture in AI to connect, not so much to connect to the outside world, but to actually inject the symbolic approaches and express it in a connectionist way. Or in other words, if I have a symbolic system, I can put very hard constraints on my system. You know, I can just follow Asimov laws. I can say, don't harm anyone, only work for humans. Can we express these hard laws in a connectionist architecture? So can we control machine learning in such a way that we limit it? I think this is the challenge that we're sort of facing. I think there's some approaches where we use Bayesian approaches in connectionist architecture that's already paving the way for this. But I think in the next decade, we'll see more and more of this. And we needed to, because these machine learning tools now, these completely connectionist architectures, they're completely unhinged. So I think we're entering into a time of a reverse symbol grounding problem. It's more of a connectionist grounding problem or something. It's like, yeah. But the merger of the two is essential to AI. Yeah.
Yeah, nice. But integrating rather than picking either or approaches.
Yes,
Yeah.
I think so.
Nice.
Yeah.
Okay, I'll do one more question from the Q&A, and then I would like to wrap up with just some fun, weird AI-generated music. And I like this one. Andre's asking, don't we overestimate maybe human understanding? And couldn't you argue that understanding is a subset of predicting future outcomes? So yeah, is accurately predicting by a machine not maybe the same as understanding, or where do you actually fundamentally see a difference between those things?
Yeah, I think it's a very complex argument to make, and I think the point that you raised is also very valid. I mean, I don't think we can prove either scientifically at the moment. For me, it feels a bit like confusing the territory with the map. So imagine you have a perfect map of the world. How do you discern the map and the world? Well, probably because there will be an error somewhere in the map, or there's an omission in the map. That's where you suddenly realize, hey, this is not the real thing. And I think it's the same with these computational architectures. We become better and better. We hardly discern them anymore. We get deep fakes. We get very intelligent machines. But at some point, they just break down or they do something weird. And that's when we realize they're not the real thing. So if we want to have the real thing, what do we need? Can we get there with computers, computational architectures? Can we get there maybe with connectionist architectures and machine learning? What if we do machine learning in the hardware? We get these chips, these AI chips going more and more. It's hard to predict where it's headed. My gut feeling is that we will never get there, like getting the real thing, if you don't have sentience somehow, because the sentience part is what gives the value. And if without having the value, there's no self, there's no point in doing something. So even though it might be very functional to us and it might be very intelligent to us, it will never be functional and intelligent to itself. So if the goal is to produce a system that's useful or has economic value, we can probably go a long way with the side of mechanical computer systems. If the goal is to have an AI in itself that is trustworthy, creative, etc., then I think we need something completely different. We're not on the track anymore. But that's my personal conviction, and I don't think there's any scientific way to actually support this at the moment.
That's all right. I think we've definitely ventured into the domain of philosophy rather than science. Yeah. And right, that's the best thing about working in AI, is that they come together.
Yeah.
Nice. Thank you so much for sharing all your thoughts on this wide range of questions as well, in addition to all the nice stories you told. We have a few more minutes. So yeah, maybe if you have a file handy, I think it would be really cool to maybe share a few minutes of the music you've worked on. People are also sharing lots of AI composers actually on the chat. So if you need those for any of your research, then let me know.
Please share them. It's interesting to take a look.
Yeah,
I have some backup slides. Let me see if we can get through them.
Cool.
No,
and otherwise, maybe just where people can check out more of your work, because I think everyone's probably curious to maybe see and read a bit more about your thoughts and the projects you're working on with designers. So where can we find more of your creations and research?
Well, there's the Asimov Institute website. So that's Asimov with a V and then Institute, which showcases some of our work and also the neural network too. There's my personal project page and our research group's project page on the Utrecht University of Applied Science. I think if you Google my name, you're probably the fastest way to get there. Some papers on ResearchGate, but most of these projects are actually not captured in papers. They're just like blog posts. There's an article on the AI arms race and geopolitics, which just came out, which is at the World Economic Forum, was published last week. So there's a couple of places, but just if you want to know something, just email me and then we can sort it out. I think that's the quickest way to do this. I'll give you some pointers.
Amazing. Yeah, if you want to share anything, we'll send an email. So I'll just pop all the links in there. So anyone who's frantically Googling right now, you can chill, and we'll send you all the links after. One last question: do you have a book on the way? Because if you don't, then maybe it's time to start writing one.
Maybe it's in here right now, so let's see. Yeah,
so on the way, just incubating.
It's on the way, exactly. Yeah. I'll try to share some of these music files, but I'm not sure if they're going to work. So I'll start with Bugbot, which I think is about 5 years old now, which was an attempt to simulate Bach's music or to generate music that sounds like Bach. So if this is the bottom one is the original Bach, let's see. Can you hear this?
Yeah, that works all right.
Yeah. See if you can spot the difference. This is Bach, and so this is what the Bugbot generated. And there's been lots of discussion going on whether this is like, is it close to Bach? Some people really don't like it. You can also, so what Bugbot did was actually approach music from the notes. So it didn't take it as, let's say, a WAV file, or it didn't sample the actual sound. It sampled the music from almost like a sheet. Yeah. And it imitated the instrument. There's also other approaches where you can, like Google did this with Magenta, where they actually emulate or simulate the sound that you're hearing. Sorry, this was still the notes. I'll give the next slide is the sound. So I'll give you another one. So this is a jazz one. So I wouldn't listen to this for an entire evening, but maybe some people would like it. So I think it
podcast intros.
Yeah, I think it sort of captures the thing, but it's like the meaning is missing, like the sentiment that is missing from this. So these are the examples where you can actually hear the AI learning the sounds, not just the notes. So that's a piece of classical music. Now, interestingly, WaveNet is actually used now for packet prediction over networks, because it also has this sort of analog property that you also have in music. So Google is finding out that they did this on creative AI, and they're applying it into very useful domains, which they hadn't even thought of beforehand. And then there's Groove, which uses a GRU unit, which is a bit like an LSTM. And I like this because it really starts out bad, and then you can hear it learning. Almost.
Sounds like noise. Yeah.
You hear a beat sort of. Let me skip a bit. All right. So this is other people's work. We did a project with DJ Gecko, who is a famous hardstyle DJ in the Netherlands, and he wanted to collaborate with us. Yeah. So, and what we did is something different from what you just heard. What we did is style transfer for audio. So you basically have a source file, music source. Then you have a style fragment, which was one of the pieces from DJ Gecko. We extract the style from the fragment, and then we apply it to the source to get the styled source. And before I press play, I'm warning you that some of these fragments are very loud, and so don't turn up your speaker too hard, especially in the next slide. Okay, let's see. So this is the source. Very familiar. This is the style fragment, sound warning. And so this is what the AI produced when it applied the style fragment to the music source. And again, this is not something you put on an album, but the funny thing is every time we work with creative people, they get very excited. We as engineers get disappointed. We say, well, this is not the end result, but they're inspired. So in this case, we produced the following style source. And so, and DJ Gecko really loved it. He said, I'm going to, this is a new sound for me. I couldn't get it out of my current instruments. And he worked on that. And then when he promoted his new album, he actually put it right up first at the soundtrack. So this is from YouTube, is the album release.
Hey, it's Gecko here, and I'm gonna play a lot of new music at Funky Cat this Friday. To give you an impression of what you can expect, I've got some samples of my new tracks. Let me know what you think of it.
Right. Well, so you can hear that. I warned you about this. Yeah, I think that's what I wanted to let you know.
Nice, amazing. I think we'll wrap with that. Thank you so much, Stefan, for sharing. And feel free to forward me any links that I can then forward to everyone who's been here. And yes, thank you so much for sharing your time, and looking forward to work on more things together. And thanks everyone for being here on our first event again of the year. We're back. We have more stuff coming up later this month and next month. So stay in touch, hang out with us on whichever social channel you like hanging out at. And we'll see you at the next one.
Ciao. Later.
Bye-bye. Thank you. Thank you, everyone. Bye.
Thank you.